So we are starting in this lecture, the beginning of chapter 31, which is on alternating current. So we're switching now from DC to AC. And I'm going to try to warn you guys repeatedly, on most exams, you're using the equation sheet holistically, and often you're using prior equation sheets as well. There is a distinct split between DC and AC. So chapter 30 was DC, chapter 31 is not going to be AC, and you cannot use equations from one chapter to do problems in the other chapter. So it's very important as you're doing problems, especially on an exam where they're mixed, that you look at what the power supply is. I will tell you, because otherwise you can't do the problem, but you also have to then make note of that. So if it says DC, use stuff we've learned prior, so topic or chapter 30. If it says AC, you want to focus in on chapter 31. Please do not mix them. So we are now going to have currents that vary, and they're going to vary periodically. So we're going to find the current as equal to the max current times the cosine of omega t. Now you can introduce a phase angle into an equation like this, but I always assume the phase angle for current is 0. That's not necessarily true, but that is how I write my problems. And we're going to talk about voltage as equal to max voltage times the cosine of omega t plus phi, where phi now is that phase angle. So we would have learned in 151 that the angular frequency is equal to 2 pi times the frequency, and typical frequencies for household circuits is 60 hertz in the US and 50 hertz in the rest of the world. So this is why if you go on vacation, you often have to buy an adapter for anything that plugs in, because you aren't operating on the same AC circuit system between the US and other countries. And in fact, it isn't even like, the textbook says 50 hertz for the rest of the world, but I don't even think it's that quite set, because I had to help a colleague purchase different adapters for a European vacation. Alright, so if we want to talk about the average current though, rather than trying to talk about a max current or a current at one specific moment, we have a little bit of a conundrum. Because remember, when you do the cosine, it varies from 1 to negative 1. So if you take 1 plus minus 1 and divide by 2, you get 0. So that means that we need to take the average in a slightly different way. And we're going to do something called a root mean square. And literally the name tells you what you're doing. You're first squaring it, then you're going to take the mean or the average, and then you're going to take the square root again to get the value. By squaring the numbers, you're getting rid of all of the negative signs, and thus you're adding together all positive values, so you won't get 0. Alright, so if I square my current function, we end up with I squared equals I squared max I squared cosine squared omega t. And we're going to take advantage of a trig identity that says the cosine squared of A is equal to 1/2 1 plus cosine of 2A. So rewriting that, I'm going to get I squared equals max I squared 1/2 1 plus cosine 2 omega t. Alright, so rearranging a little bit. Essentially I'm distributing. Now we still have a cosine in here. And so because half the values are going to be positive and half the values are going to be equally negative, this term still goes to 0 when you take the average. So we're left with I average squared equals I squared over 2. So if I take this, and I'm going to say RMS because it's really RMS, is equal to the max current squared divided by 2, taking the square root. Or we say that IRMS equals the max current divided by the square root of 2. And we could go through and do the same thing with the voltage. Alright, so what I'm trying to emphasize here is something called a phasor diagram. Since we're dealing with values that vary with time sinusoidally, we can use phasors in order to represent what the value is at one particular moment. Where you have, it's not really a vector, it's a phasor that represents what the current actually is. For example, we're going to have other max values that we're going to discuss, like the voltage. So in this example, we're talking about current. So each of these phasors, the phasor itself, the arrow would represent the magnitude of the max value, and then its angle from 0 would represent omega t, telling you what the current little I is at one particular moment. So our goal is to match this descriptions over here to the phasor that it's describing. So A here is negative current. So this side of our coordinate system that ranges from pi over 2 to 3/2 pi is our negative side. So it's negative and it's becoming more negative. So we're coming here from cosine of 90, which is 0, down to pi, which is going to be -1. So here we're going from being negative to becoming more negative. So A matches with B. In our second one, we have a positive current that's decreasing towards 0. So positive is on this side, and we want to decrease towards 0. So this cosine of 0 is 1, cosine of pi over 2 is 0, so that would be match with A. In C, we want to find a positive current that is becoming more positive. So since we're dealing with positive, we need to be on this side. And we already matched this one up, so it has to be D. And we know it's D because we're going from 3/2 pi, so that's cosine would be 0 of this, up to cosine of 0, which is 1. So we're a positive current and is becoming more positive. So this here is going to be C. For our last one, since we've already matched them up, we know it's going to be over here. But to explain why this is the answer, we're negative. So once again, negative is on this side. And we're moving towards 0. So we're going from pi, which is -1, to 3/2 pi, which is 0. So we're negative and we're moving towards 0.